Next, we are going to learn about the properties of solutions. Solutions have something called colligative properties. These are special properties that depend only upon the amount of solute or the number of solute particles in solution, but not upon the chemical identity of the solute. So it doesn't matter what the solute is, it only matters how much of it is dissolved. The four colligative properties we're going to talk about will be vapor pressure lowering, boiling point elevation, freezing point depression, and osmotic pressure. Recall that we previously learned that vapor pressure is the pressure that's exerted by a gas in equilibrium with a liquid in its closed container. Equilibrium means that the rate forward equals the rate reversed. So the liquid particles are colliding around and bouncing into one another, and eventually one of them has enough energy to jump out and make a phase transition from the liquid state into the gaseous state. In other words, it evaporates. At the same rate, though, the gas particles are also colliding around, bouncing off the walls of the container, bouncing off of one another, and one of the gas particles condenses back into the liquid state. So a gas goes back into a liquid and has condensation occur. The rate of those changes is the same, hence equilibrium. Recall that the two double arrows mean equilibrium. The vapor pressure now is the pressure that we measure of the particles that are in the gaseous state. They exert a pressure from their collisions. In this image on the right, we can imagine that maybe this is pure solvent. So this is not a solution, this is just a liquid made up of one thing. We'll see that the vapor pressure will actually change when we make a solution rather than when we have a pure solvent, as we see on the right. Whenever you measure the vapor pressure of a solution that contains a solute compared to that of a pure solvent, the vapor pressure is always lower in the solution than that of the pure solvent. If these are our particles that are representing our gaseous phase in our pure solvent, we can see that there's a lot of them above the liquid level. Now when we compare the number of particles above our solution, there's a lot less of them. Therefore, this is going to exert a lower vapor pressure in our solution. This is because the red particles, which are representing our solute particles, are blocking some of the escape of our solvent particles in our solution. Therefore, there's less solvent particles escaping to that vapor phase. Whereas on the right-hand side, it's easier for a lot of our solvent particles to escape because they're not being blocked by these solute particles in the solution. So every time we make a solution, it's going to have a lower vapor pressure compared to its pure solvent. Raoult's law will allow us to calculate the vapor pressure of a solution. It says that liquids of non-volatile solutes, meaning solutes that will not evaporate easily, will have a lower vapor pressure than that of their pure solvents. Raoult's law says the vapor pressure of the solution is equal to the mole fraction of the solvent times the vapor pressure of the pure solvent, where P solution is the vapor pressure of the solution, P0 solvent is the vapor pressure of the pure solvent, and X solvent is the mole fraction for the solvent, rather than before we were calculating the mole fraction of the solute. We're going to start out by assuming that our solutions we make are with nonionic, non-volatile solutes. So they don't easily evaporate and they don't break up into multiple particles if they're non-ionic. Later we'll learn what happens if we use an ionic solute to make a solution. Calculate the vapor pressure of a solution when 1 mole of a nonionic, non-volatile solute is added to 1 kilogram of water. The vapor pressure of pure water at 25 degrees Celsius is 23.8 torr. So this is going to be a Raoult's law problem. The vapor pressure of the new solution will equal the mole fraction of the solvent times the vapor pressure of the pure solvent. First, let's calculate the mole fraction of our solvent. That's going to be equal to the moles of our solvent, which is water in this case, so moles of water, over total number of moles. We're told that we have 1 kilogram of water. So first we're going to want to convert that 1 kilogram of water into moles. There's 1 kilogram equivalent to 1,000 grams. And then using the molar mass of water, 1 mole of water is equal to 18 grams. That gives us 55.6 moles of water. That's going to be in our numerator since we're calculating the mole fraction of the solvent this time. So 55.6 moles on the top, and then in the denominator we're putting our total number of moles. So 55.6 plus, we only added 1 mole of a nonionic nonvolatile solute. So 55.6 plus 1. Our units of moles will cancel because mole fraction is unitless. And so our mole fraction comes out to be 0.984. We're going to plug that into Raoult's law. So the vapor pressure of our new solution will equal our mole fraction, 0.984, times the vapor pressure of our pure solvent. We were told the vapor pressure of water is 23.8 torr. So when we multiply them, since mole fraction is unitless, our units of our solution for our vapor pressure will be in torr as well. And that gives us 23.4 torr. Since the vapor pressure is going to be lower, we should expect a lower number than that of the pure water. So it only dropped by 0.4, but it still is lower, and that's kind of a check you can use at the end to make sure that your answer makes sense. Given the following data, calculate the vapor pressure of the solution. We have component A and we have component B. We also know the molecular weights of both of them. Component A is present in 20 grams. Component B is present in 50 grams. That tells us that A is going to be our solute because it's present in the lesser amount, and B is going to be our solvent because it's present in the greater amount. We also know the vapor pressure of our pure solvent is 10.5 torr. This is going to be a Raoult's law problem. The vapor pressure of the solution will equal the mole fraction of the solvent times the vapor pressure of the pure solvent. First, let's convert our grams into moles. 20 grams of A, and we know that the molar mass is 278 grams per mole. So when we divide, we end up getting 0.0719 moles of component A. Starting with our 50 grams of component B, the molar mass is 144 grams per 1 mole, and we get 0.347 moles of component B. Next, we can calculate the mole fraction of our solvent, which will be mole fraction of component B. That'll be moles of B divided by our total number of moles. So B goes in the numerator, 0.347 moles, divided by 0.347 plus our moles of component A that we calculated, 0.0719 moles. Canceling out our units of moles on the top and the bottom, we end up getting a mole fraction of 0.828. Now we can plug that into Raoult's law to calculate the vapor pressure of our solution. Vapor pressure of our solution will equal our mole fraction of our solvent, 0.828, times the vapor pressure of our pure solvent, and that came from our data table, 10.5 torr. So the vapor pressure of our solution should be less than 10.5 torr because we know there's a vapor pressure lowering when we make a solution, and it comes out to about 8.70 torr. Our units are the same as what we were given because our mole fraction is unitless, but vapor pressure can be measured in a lot of units we learned: pascals, bars, atmospheres, torr, millimeters of mercury, etc. There's many units, and it doesn't matter what they're in as long as they match what your original units you were given were. Now let's try a little bit of a harder example. Given 0.454 grams of a solute dissolved in 100 grams of C6H6. This is benzene, which is an organic compound, and this is our solvent in the problem. The solution has a vapor pressure of 94.525 torr. The vapor pressure of pure benzene is 95 torr. Determine the molecular weight of the solute. So that last line tells us what we're trying to do. We're trying to determine an unknown molecular weight. And molecular weight is units of grams per mole. So if we can find grams of solute and moles of solute, we can get what we're after, which is that unknown molecular weight. In the problem, we're told that our solute has a mass of 0.454 grams. So we can plug that into the numerator already. We know the mass part. What we don't know is we don't know the number of moles of solute. So we're going to have to use the information we're given to calculate that unknown number of moles if we're going to calculate the molecular weight. Since the problem is discussing vapor pressures of solutions and solvents, this is probably going to be a Raoult's law type problem. So the vapor pressure of the solvent times the vapor or the mole fraction of the pure solvent will equal the vapor pressure of our solution. That's what Raoult's law says, but let's expand it a little bit. What's contained within our mole fraction of our solvent? So the vapor pressure of our new solution will equal the mole fraction of our solvent, which is the moles of our solvent over the moles of our solvent plus the moles of our solute times the vapor pressure of our pure solvent. Notice when we expand our mole fraction, contained within the denominator here is the moles of our solute, which that's our unknown that we need to figure out. So whenever we don't know what something is, we can call it X. We're going to be trying to figure out X, which is equal to the moles of our solute. We'll then plug it into the denominator to figure out our unknown molecular weight. We know that we have 100 grams of our solvent, C6H6, so let's convert that into moles first. We're told that the molar mass is 78 grams per mole. When we take 100 and divide by 78, we get 1.28 moles of our solvent, the benzene. We can plug in everything else as well. 95 torr is the vapor pressure of our pure solvent, so P0 solvent, and 94.525 torr, which is a little bit lower, is the vapor pressure of our solution. So we have 94.525 is equal to our moles of solvent, which we just calculated, 1.28 over our moles of solvent, 1.28, plus our moles of solute. We don't know what that is, so we're going to say plus X. That whole term will be times the vapor pressure of our pure solvent, which is 95 torr. If we divide both sides of the fraction by 95, we can isolate our term that contains our X in it. So that's going to give us 0.995 equal to 1.28 over 1.28 plus X. And if we want to move our term that has X out of the denominator, we can multiply both sides by that whole term. It'll cancel from here. and we'll end up with 1.28 plus x times 0.995, and that's equal to 1.28. Next, we have to distribute our 0.995 to the x term, and we have to distribute it over to 1.28. When we take 0.995 times 1.28, we get about 1.27 plus 0.995x, and that's equal to 1.28. We're going to isolate our x term, so we're going to subtract 1.27 from both sides. We'll get 0.995x equal to about 0.01 when we subtract. And then we're going to divide both sides by 0.995 to get our x term alone. So x comes out to being about 1.005 times 10 to the negative 2. And what that is that's our moles of solute that we just calculated. So now we can take that and we can plug that in to where we are calculating our molar mass. So our molar mass, or our molecular weight, will be 0.454 grams divided by what we just found, 1.005 times 10 to the negative 2 moles. And that comes out to right around 45 grams per mole. Now, depending upon where you round when you're calculating your x, you might end up getting a different answer for the molecular weight or for your x calculation. I redid this another way where I didn't round as much, and I got an x value of 0.006432. And that led to a molecular weight calculation of about 70 grams per mole. So you can see how different the answer is when you're carrying it through if you round versus if you don't round. And as long as you're showing me your work and I can follow along, I can follow that through and see if you did your math and your calculation right. When using Raoult's law to calculate the vapor pressure of our solution, it only works perfectly for what is termed an ideal solution. An ideal solution is one where the forces between AA, which we could imagine being our solute forces, and between BB, which we could imagine being our solvent forces, are equal to the forces that are set up between our new solute and solvent interactions, or AB forces. They are all equal. If they're all equal, that would mean when we form a solution, no heat would either be generated or absorbed. Therefore, the enthalpy, or the delta H of the solution, would be equal to 0 overall. If we look at the graph on the right, on the left-hand side, this represents the vapor pressure of pure component B, so that would be our pure solvent. And on the right-hand side, this represents the vapor pressure of pure A. So the mole fraction of A is 1 because the solution is all A, or the mole fraction is all B on the left-hand side. There's a straight line that runs between A and B, and along that way would be different mole fractions or different components of our solution making it up. The vapor pressure changes, but it always would fall perfectly along that straight line for an ideal solution. This is not really the case in the real world, but we're imagining that our solutions are ideal or close to ideal when we use Raoult's law. But in reality, the vapor pressure really might not fall along that line between the two of them. In real life, when we make a solution, there could be heat generated. We could have an exothermic or an endothermic solution that could lead to positive or negative deviations from Raoult's law when we actually calculate the real vapor pressure. Positive deviations from Raoult's law means that the vapor pressure is higher than we would expect it when we calculate it. Here's that straight line that represented that ideal vapor pressure that we get when we use Raoult's law. But in reality, maybe when we measure the vapor pressure, it really follows a curve like this, where everywhere along the way it's actually higher than what we would expect from Raoult's law. This means that the molecules in the solution are breaking away more easily than they do in the pure liquids. In other words, the forces are less strong than that of the pure solute, so AA maybe is our solute-solute forces, and BB could represent our solvent-solvent interactions. Those are stronger than the new forces set up between A and B in our solution. If the new AB forces are weaker than the individual AA and BB forces, then those intermolecular forces are weaker and the particles could break away more easily than they do in the pure liquids of AA and BB. When this happens, we end up setting up an endothermic solution. The enthalpy of solution is positive overall, and you would feel this as being cold to the touch. It would absorb heat from your hand. And this is because when A and B are mixed together, the energy given off when the new solution is created is less than the energy that was required to break away AA and BB separately, as we saw in those graphs earlier. There can also be negative deviations from Raoult's law. So here's our straight line that represents the vapor pressures that we calculate when we use Raoult's law for that ideal solution. But maybe in reality, the vapor pressure is always lower than what we calculate, and it falls somewhere along this bottom curve where everywhere along the way the vapor pressure is lower than we would expect. If that's happening, that means that the molecules are breaking away less easily this time, or they're being held more tightly in the new solution. So what that tells us about the intermolecular forces is that the new AB forces set up in our solution are actually stronger or greater than the individual AA forces of our solute and the BB forces of our solvent when they were separate. This means that when we mix A and B together and make our solution, more energy is released from the setting up of the new AB interactions than was required to break apart AA and BB. So what this means is there's energy released. The enthalpy of solution will end up being exothermic, and it'll feel hot to the touch because more energy is released when we set up those new intermolecular forces. So this is a negative deviation from Raoult's law.